Now, if it was just this simple, then probably this technology would have become outdated very long back, right? But none of the long-lived technologies are that simple, or rephrased in a better terms, none of the long-lived technologies are not good enough, right? So there are many things in which we can improve that. There are many challenges with them. There are many, with every problem or within every challenge comes an opportunity. And the technologies that have more such opportunities where we can make things better by improving some aspects, they are the ones that usually lives much longer than the technologies that does not have any scope of such improvement. They may be replaced by another version of technology quite sooner. So hard disk is definitely not on the simpler end. So let's look into, we do not have enough time to dive into all the improvements that have been done, or all interesting things that have been proposed, discussed in research articles and literature, which made the hard disk to what it is today from the time that it was invented. But surely let's look into a couple of those, and definitely feel free to dig more in the topic that you're interested in. So nobody could stop you from doing a Google search and reading and watching videos to learn more, right? So depending on your interest, feel free to dig more, but I would be discussing few important and interesting tricks in this lecture. So first interesting trick is tracks queue. Now, as the name says, it has to do something with the tracks. And as you know, like the basic English definition of or meaning of skew, it's something skewed, right? Skew is something skewed, you know it. So let's not going into the English definition of the skew. You can definitely look that up, but let's look into what do we mean by track skew, particularly for hard disk. So here in this figure, as you see that we are starting to number our blocks in the outermost track from 0. Then we are, if we keep on naming them, increasing in an incremental order in this direction. But when we come back to the same position over here, right, the last number that the last block that we can accommodate on this track is 11. So the 12 should be in the next immediate inner track. But rather than putting 12 at this location, right, rather than having 12 over here, we put 12 over here. This is exactly what is this distance is exactly what's called track skew. Now, why would somebody have track skew in their hard disk? Are you wondering that? Me as well. Put some thoughts onto that. Why do you need to have track skew, or why would having track skew be beneficial? If not, then we wouldn't have had it, right? Any ideas? Any thoughts popping in your brains? Hopefully, yes. So, as we know that while we are rotating any object, now I don't have any object to rotate besides this pen, which I don't want to fall it down. But let's say if I'm rotating this object, let's say we are playing something like truth and dare, where we are rotating the bottle, right? when I rotate this freely, if I dare to remove my hand, I'm not that stable, but it would have some additional, after I remove my hand from that, it will have some additional rotations as well. And that's just the notion of physics, law of inertia, right? The object in motion continues to be in motion. It's the same law. So when, let's say when we are writing or when we are having a data write that spans over 14 sectors. So we start from our sector 0. Let's say this hard disk is completely empty. So we start from our sector 0. Now, after we are done after we are done writing 11 sectors, it's the time to seek for a new track. Now, in order to seek this new track, we know that we would have to move our head to the new location. This motion is, everything is physical component. So this motion cannot be instantaneous, that it just happened, right? It would take some time for the head to be relocated from the outermost track to a one track inside that. Now, during this time, while the head relocates itself from the outermost track to the second track, what happens is, because the object in motion continues to be in motion, even if we stop the electric power or external power source to this disk that's already rotating while it was writing from sector 0 to sector 11, it keeps rotating. And because of this keeps rotating, if we would have had our sector 12 located at this position, then what would have happened is, by the time the head would seek from this track to this track, we would have already missed this location. And this location would have, just because of the inertia, this location would have already gone somewhere from. So then we would have to do whole another additional rotation to get that address 12 back to our head from at which we wanted to write the data. An additional rotation means additional rotation latency. So considering such minute, intricate features into the design, people invented over time, engineers came up with this idea of having track skew within the hard disk. So on an average, they studied how much a disk would rotate after they cut off the power, maybe, and how much time would it take for the seek head, for the head to relocate from one track to the another track. And depending on that, in order to have the least possible PIO, we had this track skew embedded within the design of the hard disk itself. The second interesting concept is multi-zoned disk drives. Now, if you see in this diagram, we see that there are 11 sectors in the outermost track, as well as there are 11 sectors in the innermost track, and all the three tracks. But does that sound practical, having same number of sectors in all the tracks? Well, hard disks have disks that are in the shape of circle, right? So definitely the sectors that we can accommodate in the innermost track could be less than the sectors that we can accommodate in the outermost track. The area that we get in the outermost track is, by the shape of circle, higher than the area that you would get in the innermost track. It's just that there's a lot more space out there, right? So why don't we make use of this lot more space to store a lot more data rather than storing the same number of sectors on all the tracks. The idea behind multi-zone disk drives was exactly, if you have a lot more space, let's build a lot more rooms, right? So let's accommodate a lot more sectors in the tracks, in the outer tracks rather than inner tracks. So what we did was having multiple tracks. Again, my circles are very perfect, so do please appreciate my circles. If the hard disk is actually of the shape, I don't know if that hard disk would work or not. But well, it's good enough to explain you the idea. So I'm happy for that. So in multi-zone disk drives, we divided the tracks into different zones. Let's say the outer two tracks frames zone 1, then the next two frames zone 2, and then we have next two that frames zone 3. So here we have 3 zones, Z1, Z2, Z3. And each zone consists of 2 tracks. And so rather than sticking to fixed number of sectors that resides on each track, now we modified the disk to have fixed number of sectors within each zone. On the other hand, different zones can have different number of sectors, and logically, we would have more sectors in the zone that are near to the outside of the disk versus the zones that are in the interior portion of the disk will have less sectors. So again, a very simple but a brilliant idea, right? Isn't it? We are able to store more data in less space. So our hard disk would look of the same size, but hola, it has double the capacity. Rather than storing 2 terabytes, now we are able to store 4 terabytes on that same size disk. So a simple idea could make a big difference. And these are really live examples of how storage systems have evolved with small, simple ideas built upon each other. Third, and another important idea is something that's called track buffer or cache. It is also called as write-back caching or write-through caching. Now, this is the concept of having some memory on the disk where, let's say that we have our disk, we have some on-chip memory. It's different from the system memory. Please remember that. On-chip memory. And we have our CPU processes. Now, write-back caching is again same as what you would have learned in your operating systems concept. Do you remember what's the difference between write-through caching and write-back caching? Well, I hope yes. If not, then you better pay attention and do not forget from here. So write-through caching is something where the CPU process would write to the memory, on-chip memory, but it wouldn't return immediately. It needs to write through this on-chip main memory all the way to disk, and only then it would return back. So this is write-through caching. As the name says, write through. So do not return in the between, in somewhere in intermediate state. Write it all the way through the end and then return back. Write-back caching, on the other hand, is another way where CPU process would just put the data that it wants to write on the disk in the on-chip memory and return right back. Come right back, right? Our mom used to ask us to get some things, or maybe they still ask us to get them some things and they don't want us to spend time in grocery store just to be late at home, or they don't want us to get distracted to meet our friends on the way. So what would our mom say? Come right back. So anything that's like urgent, come fast, come as soon as you are done with that first step, right? That should ring the bell in your mind, write back caching. So write back is we just put the data on chip memory and then go back, and then the process returns. There are definitely advantages of write back caching, as you would have already been thinking that it's fast because you don't have to wait all the way through the end. And writing to the disk is definitely time consuming. Why? Because as we just learned, it includes that time to seek, time to rotate, time to transfer, all that. So we don't have to worry about all these time to seek, time to rotate, and time to transfer, but rather as soon as the data is on-chip memory, then we could return the process. So write back caching is definitely performance efficient. But there is always a caveat, right? There is always a trade-off. What's the trade-off here? Let's say you put some data on chip memory and there was this power outage. And because of the power outage, your system just shut down. Maybe you didn't have external backup battery or any other power source after the power outage to deal with the power outage. And at that exact moment of power outage, the CPU process would have put your data on chip memory, but that data is not yet returned to the disk. What happens then? Because the on-chip memory is not persistent, the data just vanish. And when power comes back again, it says, sorry, there's no data. You didn't write anything. Now, if this write is just a hello world program and writing that to file, probably you could just run that program again. But if this write is your salary transfer from your institute or from your workplace to you, where workplace sees that they have already transferred salary into your account, where this is your account, and you didn't receive the salary for that month, you go back to the workplace and say that, hey, I didn't receive the salary for this month. And they are like, no, we already transferred. What a big disaster would it be, right? So write back caching could lead to as big disaster as maybe not getting paid for a month if it doesn't go well. While write-through caching is definitely way more reliable in the sense, even in case of power outage, because either a process would say that the data is safely returned, or it would say that it's not returned. So in the same example of salary from your work institute to you, in case if they were using write-through caching, or the banking services were using write-through caching, which most of them they should be, right? Don't know, well, we don't work for bank. Maybe some of you work for bank, so you can ask to the data center management team of banks. But well, I don't know what they actually use. Hopefully they are using write-through caching, because I don't want to risk with write-back caching. But what happens in that case is, if you don't see that the money being deposited or it being returned to the disk, you go back to the institute and they would agree with you that yes, data is not returned. And they would say that, oh, sorry, there was a crash or a glitch, but we have already reprocessed it and you would be receiving your salary in maybe a couple of hours by the end of the day, something like that. So not much of a problem if you're using write-through caching. Again, this small improvement of having different ways to deal with writes by having this on-chip memory, and how do we make use of this on-chip memory is gives us an opportunity to tweak as per the situation, right?